Welcome to this explainer. Today, we're unpacking a truly elegant mathematical tool called Principal Component Analysis, or PCA for short. Now, if you're regularly working with massive datasets, you might be looking at PCA as this daunting, heavy math problem. But I want to reframe that for you. Think of PCA more like a really powerful lens. It's a tool that helps us find the true signal hidden inside extremely messy, high-dimensional data. It literally allows us to clear away all the clutter and see the fundamental structure underneath.
Okay, so here's our roadmap for the explainer today. We'll be hitting 1. Data overload and hidden redundancies, 2. Pre-processing, 3. Finding the major axis, 4. The math, and finally 5. Real-world applications. Let's dive in.
Section 1. Data overload and hidden redundancies. To really get why PCA is so valuable, we first have to expose a pretty massive flaw in how we usually handle large datasets. There's this common misconception that more data automatically equals more information.
Imagine you're handed a huge data set, right? It's got attributes for hundreds of different cars. You've got maximum speed, turn radius, the number of seats, the whole shebang. But what happens when some of these attributes are actually telling us the exact same thing without us realizing it? How do we automatically detect and cut out that redundancy without having to manually sift through thousands of columns?
Let's look at a classic example here. Imagine, completely by accident, our car dataset has one attribute measuring top speed in miles per hour and a second one measuring top speed in kilometers per hour. These two attributes are basically linearly dependent. Aside from tiny little differences from rounding numbers, they are identical information. Because of this, our data doesn't actually need two separate variables. It really just lies on a lower dimensional subspace.
What's really fascinating is how this concept pops up in human behavior too. Think about a survey of radio-controlled helicopter pilots. One attribute measures their flying skill, and another measures how much they enjoy it. Well, RC helicopters are notoriously tricky to fly. Because of that steep learning curve, only the super committed students, the ones who truly enjoy it, actually become highly skilled. So these two attributes end up being incredibly strongly correlated. They essentially form a single underlying diagonal axis that we might playfully call the pilot's intrinsic karma. So what is our main goal here? Well, our objective with PCA is to automatically find this specific diagonal direction. We want to find this major axis of variation where the data actually lives. We're trying to lock on to that core karma, the true signal, and confidently throw out the tiny amount of noise that just kind of drifts off this main axis.
Section 2. Pre-processing, normalizing the data. Now, before we can magically find that major axis, we have to prep our data. We need to level the playing field so that wildly different data attributes can actually be compared fairly.
We do this through a pretty standard 4-step pre-processing routine. First, we calculate the mean of our data. Second, we replace each data point by subtracting that mean, basically zeroing out the mean of the entire dataset. Third, we calculate the variance. And fourth, actually, more specifically, we divide by the standard deviation to rescale the data to unit variance. Why go through all this trouble? Well, if one attribute is a car's top speed in the hundreds, and another is the number of seats, which is just 2 to 4, the speed numbers would totally dominate the math just because they're bigger. This normalization ensures every attribute gets treated on the exact same scale.
But hey, you don't always have to rigidly follow every single step. For instance, you can totally skip the first 2 steps if you already know your data has a zero mean, which is common in certain acoustic or speech time series data. And you can skip the rescaling steps if you know up front that all your attributes already share the same scale. A perfect example of this is a dataset of grayscale images. Every single data point is just a pixel intensity from 0 to 255, so they're already on an even playing field. Moving on to Section 3, finding the major axis. Now that our data is properly normalized, we're at the core visual intuition of PCA. This is where we figure out exactly how to project our data. We know our data has a certain starting amount of variance, or information. We want to approximate this data by dropping it onto a lower dimensional line, a unit vector. But how do we pick the absolute best direction for that vector so we don't lose the essence of what our data is telling us?
This brings us to a brilliant core rule. Think about 2 possible options for a second. If we project our data onto one specific line, the points might stay nicely spread out. They retain a large variance and stay far from 0. But if we project them onto a different line, the points might just squish together, drastically dropping in variance and clustering meaninglessly around the origin. With PCA, we must always choose the direction where the projected data retains as much variance, meaning as much information, as humanly possible.
Section 4. The math. Principal eigenvectors. Once you intuitively grasp that the whole game is about maximizing the variance of our projections, the math just becomes a formalization of your common sense. We are hunting for that optimal one-dimensional subspace.
So the absolutely crucial takeaway here is that when we set up our math to maximize this projection variance, keeping in mind our direction has to be a unit vector, it naturally leads us to one very specific calculation. It gives us the principal eigenvector of the empirical covariance matrix of our data. We usually denote that matrix with the Greek letter sigma. It's an incredibly direct solution. You don't need messy iterative algorithms. You can compute it easily with standard programming libraries.
Now, in practice, we usually want to reduce our data to a subspace that's larger than just one single dimension, but still much, much smaller than what we started with. We call this target dimension k, and our original huge dimension n. So k is much less than n. To project our data down into a k-dimensional subspace, we simply calculate that empirical covariance matrix and then grab its top k eigenvectors. It's really that straightforward.
These top eigenvectors then become the brand new foundation for our data. Because the covariance matrix is symmetric, these vectors naturally form a new orthogonal basis. So, instead of mapping our data across thousands of highly redundant dimensions, we represent it purely in this new, streamlined basis. It effectively shrinks our data's footprint while keeping the absolute maximum amount of variability perfectly intact. Mathematically speaking, choosing this basis is identical to picking the subspace that strictly minimizes the approximation error when we project our data onto it.
Section 5. Real-world applications of PCA. Let's get to the real payoff and see how this elegant mathematical engine solves actual, complex problems out in the wild.
PCA basically has three major superpowers. First is data compression and visualization. If you have hundreds of dimensions of car attributes, reducing them to just 2 or 3 dimensions lets you easily plot the data and physically see which cars cluster together. Second, it is a massive help as a pre-processing step for supervised learning. Feeding a machine learning algorithm thousands of dimensions is a one-way ticket to overfitting. PCA cuts down the complexity, making learning way faster and far more robust. And third, it is a highly effective noise reduction algorithm.
A truly cinematic example of this noise reduction is the Eigenfaces method used in facial recognition. Imagine a dataset where each data point is just a 100 by 100 pixel image of the human face. That is a 10,000 dimensional vector. By using PCA, we can represent each face with a remarkably lower dimensional vector. The top principal components grab on to the systematic variations, the core structure of what a specific person actually looks like, while magically throwing out the noise caused by, say, a minor lighting change or a slight photographic angle. This lets us measure the distance between faces in a dramatically reduced space, creating a surprisingly accurate face matching system.
We've seen how PCA effortlessly uncovers the intrinsic truth hidden inside data, whether it's the karma of helicopter pilots or the core identity hiding in a photograph, which leaves us with a pretty provocative thought. If a highly complex 10,000-dimensional human face can be confidently boiled down to just a few principal components without losing its identity, how much redundant noise is secretly hiding in your own datasets, just waiting to be cleared away? Thanks for exploring principal component analysis with me today.